All right, everyone, we're back for our for another session of bivariate methods. This time we're talking about analysis of variance. Sometimes goes by the name ANOVA or F-test. So why an F-test or ANOVA? The purpose of an F-test or ANOVA is to test multiple means. What you need here basically are data that can produce a mean score. Also need some sort of categories, different types of things happening. Now, typically an ANOVA is not something we spend a whole lot of time on, but I do want to walk through it because the logic of an analysis of variance is very similar to what we will see with our multivariate regression models. They look very similar under the hood. The general form of an ANOVA looks like this. It is the total sum of squares equals the explained sum of squares and the unexplained sum of squares. There are a couple things that are really interesting here. First is that what we're trying to do is we're trying to understand the amount of variation that can be explained by a particular variable, one independent variable, right? And we're also able to identify random noise. That's the unexplained sum of squares. So random noise or error, however you want to conceive of it, it's all the stuff that we can't explain. So it's variation that is not due to changes in the independent variable. This is really important because we'll see this again with regression. There's a lot more under the hood. And as you'll see, that total sums of squares equation is sort of a generic equation. Underneath, there's an algorithm, and you can see it listed here. So for each element, for instance, the total sum of squares, let's say for the total sum of squares right here, the algorithm is the sum of x, right, which is an observation in a category, minus x mean, which is the mean of the independent variable. Sorry, this should be x sub I right here. Right now they look like they're close together. Okay, so that's the total sum of squares. For the explained sum of squares, and I try to write this over here in the bottom, you're basically looking at the sum, right? Summing up the mean of x and subtracting it from the grand mean. Okay? So what is the grand mean? The grand mean is the mean for all of the data points, irrespective of the independent variable. So all of the observations thrown in there create a grand mean. And we also have a mean that is associated with an independent variable. That's the mean of x right here. The unexplained sum of squares, for instance, is the summing up for each category and then summing up all the categories added together. All right, this sounds maybe like a lot, but we're going to walk through it in just a second. Let's say we're concerned with cheating on an exam. So we make up 3 different exams that cover the same material. So you get the following results, and what you find is that the scores, just eyeballing it, that the scores for test form 3 look not great, right? So you're trying to see whether or not test form 3 is systematically more difficult than the other 2. So your question here is, was test number 3 harder than the other 2, or was the lower mean associated with test form 3 right here? Oh, sorry, that's a sum. The lower mean, is that due just to chance? Okay, so the way in which we get at this, so this is under the hood analysis of variance. The first step we take is we sum up all the columns for each of the test forms. So for test form 1, you're going to get a sum, so you're adding up all those scores, of 16. For test form 2, it's 18, and for test form 3, it's 10. Your next step is to get a grand mean. That is the mean for all of the observations. So it includes all the columns. So once I've got means or sums for each of the columns, I just sum that up again and divide it by 12, which is the number of observations I have, which gives me a grand mean of 3.7. All right, second step. And you can do this, you can approach this a couple different ways, but we're going to do it kind of in order. So we're going to calculate the total sum of squares. So we're trying to get at the total variance that we have in this data, irrespective of the independent variables. How do we do this? We sum up the x, right? So that's you're gonna get the x Feels like there's a piece missing there. Hold on. Okay, so for the total sum of squares, you're going to get the observation in that category, and you're going to subtract it from that grand mean, right? So let's go forward here a second. So observation, so your first observation in that data set was a 5, the second one was a 4, a 2, and a 5. So this first number here is each observation, so each score associated with each test form. So each score associated with the test form, and you're going to subtract it from the grand mean and square that particular, you're going to square that number, and you're going to get something like you see here for each of these test forms. Okay, so step 1, you're going to get all of those, and once you get all of these squares, you're going to add them all up, which actually leads you to a total sum of squares of 24.68. Your next step is to calculate the explained sum of squares. So what you're trying to get at here is how much is explained by that independent variable. So now you're setting this up a little bit differently. For each test form, right, so this is test form number 1, you have an n of 4, that's the number of observations you have. The group mean for that test, subtracted from the grand mean, and squared. You'll do that for test form 2, again, n of 4, group mean of 4.5, a grand mean of 3.7, and you'll do that again for test form number 3. So in the end, it looks like this little calculation here. So you get a 0.36, 2.56, and a 5.76, which adds up to an explained sum of squares of 8.68. Step 4 is optional, and you'll see why. You may already figure out why step 4 is optional. Obviously, total sum of squares equals explained sum of squares plus the unexplained sum of squares. So you can really solve for the unexplained sum of squares by just moving the pieces around. But if you wanted to calculate the unexplained sum of squares, you do so with this general algorithm here, which is you're summing the sums of this little process here, wherein for each of these, so we're going to do this with just one example here. So for test form number 1, your first observation is a 5, that's that first score. You're going to subtract it from the group mean, the mean for that test only, and square it. Okay, that's the general pattern. If you were to do this with all the data, you would do this for test form 1, test form 2, test form 3, and you would get a result for each of those test forms. In this case, for test form 1, you get a 6, test form 2, you get a 5, test form 3, you get another 5. And you sum all of that up. So that gives you what you're looking for there, which is the unexplained sum of squares. All right, here what you're going to notice is I've got some extra notation. So sometimes, and this might be true for a variety of different sources, they refer to the explained sum of squares as the between sum of squares, and the unexplained sum of squares as the within sum of squares. Okay, so you can put all these pieces together. 24.68 equals 8.68 plus 16. It should all add up. All right, so now what? Well, ultimately what you're interested in is whether or not these mean scores are different across the test forms. So you need to find out whether or not this is statistically significant. In order to do this, you take each element of that equation that you just produced right there, and you divide them by the degrees of freedom for each component. So the degrees of freedom for the total sum of squares is n minus 1. In this case, our n is 12, so n minus 1 is 11. So you would take that total sum of squares number and divide it by 11. For the next component, the explained sum of squares over the between sum of squares, the explained sum of squares or between sum of squares, the degrees of freedom is k minus 1. K, you might recall, refers to the number of categories, right? So in this case, we had 3 tests, so that's 3 categories, minus 1 would give you 2. For the unexplained sum of squares, or within sum of squares, the degrees of freedom is determined by n minus k, and is the number of observations 12 minus k, which is 3, which gives you 9. So you're taking each component part. This was the total sum of squares. That was the explained sum of squares and the unexplained sum of squares, dividing them by their degrees of freedom to provide you these nice simple little numbers. Once you get that, you take that information and put it into what's known as the F ratio, which is the mean explained sum of squares over the mean unexplained sum of squares. So the mean explained sum of squares, in this case, you see this right here, so the explained sum of squares, when you've done that, that is your numerator, and the unexplained sum of squares, the mean unexplained sum of squares, goes right there. That's your denominator, okay, which gives you the number 2.44. You would compare this to the critical value in your F chart. Now, we've kind of done a little practice with this with a couple of our other tests so far, and this is really no different from what we had already done in terms of getting at that critical value. We're not going to walk through it right here because I'm less interested in going through the chart for this one and identifying the critical value. Okay, let's just say it's statistically significant. Here's what I'm more interested in getting at, okay? Which is getting at the eta squared, okay? So beyond statistical significance, it's also useful to know just how strong the relationship might be, okay? In this case, we do have a statistically significant finding. So if we reject the null hypothesis in step 1, the second question is, how strong is that relationship? In other words, if you recall PLS 215, one of the first things we had you do was create a research question that asked basically what explains the variation in whatever dependent variable you're interested in. Well, we're kind of interested in that same question, and how we do that with an analysis of variance is we get the eta squared, which is symbolized by this funky little n, squared. And the eta squared is determined by the explained sum of squares over the total sum of squares. Okay, so we're going to use the same example we have been walking through earlier, and we're going to put the explained sum of squares, 8.68, over the total sum of squares, which is 24.68, and it gives us the following number. What do we do with this number? Well, this number actually speaks in a language that is familiar to us. It basically says in percentage that 35.17% of the variation in the dependent variable, or test scores, is due to the variation in the independent variable, or the test form. Does this sound like your research question is being answered? Yes. Yes, it does. So part of the reason why I like the analysis of variance is that there is a certain process and algorithm underneath it, which we're going to see again for ordinary least squares regression. And second, which is that the eta squared statistic that flows from the calculation of analysis of variance actually answers a question that we have asked in 215, and would be the kind of answer to your question if you had means, if you were to conduct an F test. I'd be far more interested. Okay, so you've got statistically significant finding, you know that there's some difference, but the next step is, how much are you explaining based on that particular independent variable? And the answer here is 35.17. All right. Well, as far as I'm concerned, that is it for today. And we will see you next time when we do some practice in the lab with all this. All right. See you soon.